So it turns out that we are going to be going over some examples today. 4 examples, as a matter of fact. This is the first one. They are all related to implicit differentiation, some various subtleties of it, like this first problem here. So no need to hesitate here. Let's just go ahead and jump in and get started. And I'm going to start off with this example here because basically I'm asking for the derivative at a specific point. That shouldn't be very hard. I know I can plug in the point at the end, but I wanted to show you one nice little trick. First off, when you're taking the derivative of this, remember the derivative of y is going to be 1, y to the 0 power, dy dx. It's just going to be dy dx. And then I also use this problem because, right here, as I'm looking at it, this next part is an example of a chain rule. All that little bit in there that I just highlighted in yellow, that is just another, it's another function inside of the square root. So I am going to take the derivative of that square root. The square root's like something to the 1/2 power. So I'm going to take xy. I'm going to take that to the 1/2 power. I'm going to erase that scribble I made earlier because it's in the way. But then I want to concentrate because when you do the chain rule, whoa, that was not supposed to happen. When you do the chain rule, let's try this again. You take the derivative of the outside function. I guess the outside function was, the square root of u. And then you figure out what u's equal to, and you take the derivative of that. So the derivative of the first part was just using a power rule. The derivative of the second part is a product rule. The derivative of x times y plus the derivative of y times x. And when you do the chain rule, you take that first derivative of the outer function times the derivative of the inner function. Tell you what, I'm going to go ahead and erase that, take a nice look at it because it's going to go away, but I'm going to put that same information, the derivative of the inside function, the derivative of x times y plus the derivative of y times x in there. And then I'll go ahead and finish out this derivative. Well, the derivative is equal to 2. The derivative of 2 being a constant, is 0. Now, there is a lot of solving here, and I would love to go through the algebra of it. But here's the main point I wanted to make when I brought up this problem. The fact that we are finding the derivative at 2 means that I can actually, instead of waiting, I can plug 2 and 2 right in if I want. It actually will make the math a little bit easier. So now I've got 1/2 2 times 2, because x is 2 and y is 2. I've got 1 times the y value, the derivative times the x value, and it equals 0. Once again, simplifying just a little bit more, we've got all the numbers in here. This is nothing more than the square root of 4 down in the denominator, and then it's times 2 plus 2 of the derivative. You know what? It's still a little messy, but it sure beats having to do this without the numbers plugged in already. I'm going to go ahead and distribute this. I'm going to multiply 1/4 times each of those. So I get not that color. I get 1/4 times 2 plus 1/4 times 2 dy dx. When I get done combining like terms, I'll find out that dy dx will eventually be -1/3. So here's the lesson. I want you to remember, if you were ever finding the derivative at a specific point, or maybe you're even writing the equation of a tangent line, which is quite possible, you can plug that number 2 in first. You don't have to solve for dy dx right away.